In the last episode, I discussed the overall rationale for Urbit's design at a high level, and some of the sort of basic ideas of what it is, and how it interacts with the rest of the world, and why one person might want to run it. In this episode, I'm going to drill down a little more into the design of the system itself, and in particular, the rationale for some of the design decisions around versioning and the way we think about timelessness in software. Urbit thinks about timelessness in a pretty different way from other software systems. It's not by any means the first software system to try to produce a standard that will last for a long time. But the scope of the standard that Urbit is trying to instantiate is much larger than previous attempts and more explicit and intended to last longer, and it's also intended to be extensible. So one way of thinking about Urbit that I think is productive is to think of it as trying to standardize the operating system and to provide a standard for further standardization of new routines, new applications, services, and sort of new pieces of software. And this is intended to end up with a different sort of world of software and from the one that exists. In particular, have it add new standard protocols, standard applications, standard data structures that build on the previous ones. And so we have a system that adds layers on top of itself, but each of those layers eventually standardizes. Mostly, with some caveats. Obviously, some things are going to have to change forever. So the other way of thinking about Urbit is anything in software that can be productively standardized in a timeless way should be standardized in a timeless way inside of Urbit. And Urbit provides a language for expressing those standards. So this is all very abstract so far. I'm going to bring it down a bit more concrete. But before I do, I'm going to contrast our approach with more traditional software engineering approaches to timelessness. More traditional software approaches to design in general, which attempt to achieve timelessness by making the software easy to modify indefinitely, rather than having the software itself at a particular layer freeze such that things can be built on top of it, but have that layer actually become a frozen standard. So, give a couple examples of how this is normally thought about. I'll start from the classic Refactoring by Martin Fowler. Great book. And in the first chapter, he writes, quote, "The true test of good code is how easy it is to change it," unquote. And I might actually give you a little bit more context here. So, okay, another quote. "Programmers love to argue about what good code looks like. I know some people object to my preference for small, well-named functions. If we consider this to be a matter of aesthetics, where nothing is either good or bad, but thinking makes it so, we lack any guide but personal taste. I believe, however, that we can go beyond taste and say that the true test of good code is how easy it is to change it. Code should be obvious. When someone needs to make a change, they should be able to find the code to be changed easily and to make the change quickly without introducing any errors. A healthy code base maximizes our productivity, allowing us to build more features for our users both faster and more cheaply." End quote. So you see that his idea of code quality is about how easy it is for that code to be changed, right? And what's interesting to me about this is that he's usually right, right? I mean, this is, I think, right, this book is part of the sort of agile programming, agile software development revolution that happened in the 90s and 2000s. And I think it was an important intellectual step for software to take as an engineering discipline. And as Fowler and others write about, when people first started doing software engineering in 40s, 50s, 60s, 70s, they thought of it as sort of just another field of engineering, and they approached it the way that people approach physical engineering, such as civil engineering, mechanical engineering, electrical, etc. And so they did what was a process called waterfall development, where they start out by fully designing the system that they're going to build, which in software means laying out the major modules, what application programming interfaces, APIs, those modules will expose to the other modules, right? So so basically defining the interaction between all these modules. And there's generally a somewhat hierarchical structure where one module might have sub-modules inside of it that it manages in some certain way. And so there's this whole kind of tree of components with defined sets of interactions and their semantics, their behavior, is also defined up front before they're actually written. So before they're written in code, people would write out the entire design. And the idea of waterfall development is that, like in physical engineering, that specification, or that design spec, should be enough to allow people to actually go and implement that spec, and then once you test and make sure that the code actually implements the spec, then you're done. And for decades, this was the standard in how software was developed, more or less. But there were really big problems with this for, I think, basically two big reasons. One is that because software is actually malleable and doesn't depend on physical constraints very much, there are some physical constraints involving the CPU and max memory capacity and whatnot. But often those aren't the limiting factors of a design, and there are other limiting factors, which is just trying to make the damn thing work. Often it's harder. So, and what gets in the way of it working is usually complexity. And that complexity, different people will define that in different ways, but more or less it has to do with how difficult the piece of code is to understand, and possibly how difficult it is to modify it. So to bring up another source, John Oosterhout's A Philosophy of Software Design, also an interesting book. I'm going to quote from here, because he talks about the waterfall model also. Quote, "Unfortunately, the waterfall model rarely works well for software. Software systems are intrinsically more complex than physical systems. It isn't possible to visualize the design for a large software system well enough to understand all of its implications before building anything. As a result, the initial design will have many problems. The problems do not become apparent until implementation is well underway. However, the waterfall model is not structured to accommodate major design changes at this point. For example, the designers may have moved on to other projects. Thus, developers try to patch around the problems without changing the overall design. This results in an explosion of complexity. Because of these issues, most software development projects today use an incremental approach such as agile development, in which the initial design focuses on a small subset of the overall functionality. This subset is designed, implemented, and then evaluated. Problems with the original design are discovered and corrected, then a few more features are designed, implemented, and evaluated. Each iteration exposes problems with the existing design. which are fixed before the next set of features is designed. By spreading out the design in this way, problems with the initial design can be fixed while the system is still small. Later features benefit from experience gained during the implementation of earlier features, so they have fewer problems. The incremental approach works for software because software is malleable enough to allow significant design changes partway through implementation. In contrast, major design changes are much more challenging for physical systems. For example, it would not be practical to change the number of towers supporting a bridge in the middle of construction. Incremental development means that software design is never done. Design happens continuously over the life of a system. Developers should always be thinking about design issues. Incremental development also means continuous redesign. The initial design for a system or component is almost never the best one. Experience inevitably shows better ways to do things. Unquote. So, again, Oosterhout, in addition to Fowler, and they're saying basically the same thing, and they're both right in general. Urbit departs from this, though. Because in Urbit, we say, no, we're not going to continuously modify this thing forever. In fact, we're going to give ourselves a fixed number of changes that we will allow ourselves to make, after which the software will be frozen and we will not be able to change it. So this is the idea of Kelvin versioning, which I described in the last episode. But yeah, it's that you start from some number, 200 or something like that. I believe the sort of overall Arvo kernel, including all of the whole sort of the kernel at writ large, is at just over 400 Kelvin version. Nock, our machine code, is at version 4. So there are only 4 more changes that can ever be made to Nock. We may never make any more changes to Nock. We'll see. I wouldn't be surprised if we make maybe 1 more, but we may actually never get down to 0, which is itself interesting. So Kelvin versioning, it represents a departure from this agile mindset, because instead of saying we're going to design the system to be modified forever, we say no, after we do these 400 modifications, this thing won't ever be changed at all. So then if you start, so let's take this as the premise of Urbit, actually, right? Let's say that, and in fact, some of the initial blog posts were very explicit that this is the premise, that with Urbit, we're trying to create a system where it actually won't need to be changed. So we're trying to actually get it right in a permanent way, where even as the world changes, the software itself won't need to change. Very ambitious. And so then there's this question of, well, if you accept that premise, then how should you design the software? And a few things fall out of this. A lot of things fall out of this, actually. This is the sort of the prime directive that we fall back on when trying to make difficult design decisions in Urbit. Is, okay, well, what is most likely to last? What's a design that won't have to be changed? It's the exact opposite of Agile in some way, right? As opposed to saying, okay, this code's going to need to be changed, so let's write it in such a way where it can be maximally changed as quickly as possible. We're saying, no, okay, we're going to have to change this a couple hundred times, because actually, yeah, waterfall development, even for Urbit, is not really feasible, especially not for the system as a whole. And so, yeah, we have to give ourselves a budget of changes. We have to actually accept that we're not going to get the whole thing right the first try. But we're going to force ourselves to be on the path to getting it right, and we're going to have to get it right within a few hundred revisions, which will probably happen over the next few decades, mostly. Probably slowing down as it gets closer to Kelvin 0, just as Nock has already slowed down as it gets closer to Kelvin 0. So okay, we're going to give ourselves a budget so that we don't do full waterfall, and we can correct the initial design. But the final version of the Arvo kernel actually won't ever need to be changed at all. And so its design doesn't need to provide for such changes. And a lot of interesting things fall out of this. So one is the idea of polymorphism. I think this is just to kind of bring it down a little bit more concretely, or to something a little bit more concrete. Often, one of the sort of hallmarks of object-oriented programming and agile design is the idea that you should write each of the pieces of your system to be maximally general, so that, let's say, you write some math routine, and maybe you want that to, you write it for the problem that you're working on. You need to be manipulating integers, whole numbers, but maybe you want to say, you know what, actually any kind of number should be able to be manipulated in this way. So I'll instead write my routine in such a way that it's polymorphic with respect to what kind of number I'm manipulating, and there'll be some sort of generic interface that any number will expose to other pieces of code so that it can be manipulated in certain ways. And I'll just write my routine to manipulate anything that conforms to that interface, anything that can be treated as a number. I'll write my code in such a way that it will still work for anything that is sort of vaguely number-like. So this idea of sort of maximizing polymorphism, it is actually a useful technique, and we do use it inside of Urbit. But we don't use it as much. And part of the reason for that is that there are many cases where, when we're having some particular routine in the system code, something that, for example, deserializes a message, a network message, right? We receive a network message as just a bunch of bytes, and we want to convert that into a data structure that Urbit understands, right? So a noun, right? A tree. And, when we do that, there's an interesting thing where we don't need that to be polymorphic. That piece of functionality is going to be frozen. We don't need to also be able to convert that into some other representation, right? Convert those bytes into something that's not a noun, right? So this doesn't need to be polymorphic. And there are tons of examples like this, actually, where it's like, because we're building a specific piece of code in the kernel, right? Sometimes I've been a little imprecise with the term kernel and system here, but what I mean is really the standardized part of the operating system. So the part of Urbit that's written in Hoon, so it compiles to Nock, and it's the specification for the behavior of the Urbit operating system. So that spec, that's the Kelvin version of that will go to 0 eventually. And that includes the kernel proper, the Arvo kernel proper, which basically knows how to run the kernel modules and run other code. So it knows how to run the kernel modules, and it knows how to upgrade itself to the next version, and how to upgrade the language, the Hoon language. So that's what the kernel proper does. And then the kernel sort of writ large includes a number of kernel modules called vanes, V-A-N-E-S. There are about 8 vanes, and most of them are for dealing with for various input-output channels. So there's a vane for AIMS, the Urbit to Urbit networking, a vane for EYRE, E-Y-R-E, the Urbit's HTTP interface for communicating with the old world. One is for DIL, which is terminal interaction, command line interaction. And then there's also Gall, and Gall is responsible for running apps inside of Urbit. So it's the application runner. So anyway, that's the kernel writ large, is those. And the kernel proper is just Arvo itself, just the piece of that runs the vanes and upgrades itself. Okay, just a little background there. But the kernel writ large is Kelvin versioned, and that entire thing is going to go down to 0. So not just the kernel proper, but everything else in there. And so this means that all of that code is specific. All it ever has to do is deal with those specific input-output channels, implement the specific behaviors that are required of this operating system, and know how to run applications using a generic application runner interface. So basically there's a certain way that an app can be built from source code and turned into a program. There's a certain way that once it is a program, there are certain kinds of requests that it can emit to the operating system, defined as just data types, right? It can just return a piece of data, and then the kernel will interpret that piece of data as a request to perform some action. And there are only certain kinds of data that the kernel will ever give back to that app as a response to one of its requests. So now there might be some polymorphism that shows up in that application runner interface, right? It's not that there's no polymorphism, and this is sort of one example of the difference between Urbit and other systems. We do actually have some polymorphism. It's appropriate for some cases, in particular cases where there will be future extension, or where there are already so many examples of code, even just in this specific kernel, doing basically the same thing but with different data types, that it's a more concise and clear way of expressing the behavior by writing a polymorphic function. So, for example, there are list manipulation routines in the standard library, and you can have a list of integers, or you can have a list of pairs, and the list manipulation routines are properly polymorphic in that they're just for manipulating the list, not about looking into the items. So I'm not saying that there's no polymorphism. I'm saying that the way we think about polymorphism is one example of a difference between Urbit and other systems. And it's not the only difference. Our system is sort of less, it looks less like an exploded diagram than a lot of systems do. So when you read the kernel source, if you understand Hoon, if you're familiar with Hoon, when you read the kernel source, you generally get a relatively clear picture of the overall shape of the operating system. And that shape is clearer, actually, than in a lot of other systems where the pieces have been broken out they've been sort of scattered. I think this is especially a problem when you look at code that's written using test-driven development. That because you need to be able to test each individual function on its own in that paradigm, you end up sort of breaking things apart that maybe naturally wouldn't be broken apart, except that you wanted to test some piece of it individually. So Urbit does have unit tests, quite a few actually, and since Urbit, the whole system, is deterministic, you get deterministic unit tests. Really nice. In my previous job, I actually spent a long time writing unit tests for a system that was highly concurrent with a lot of multi-threading and multi-processing and timeouts, and I was able to get a lot of those unit tests to actually work, but it was interesting that the amount of effort required to mock the concurrency or otherwise deal with it, there was so much complexity in that it actually reduced the utility of writing unit tests for highly concurrent code down to the point where I don't think it was really worth it. And it was really just worth it to test the individual leaves of the abstract syntax tree, right? The smaller routines. Those were worth unit testing for sure. But the way in which they were composed, unit testing wasn't really the right solution. And this is, of course, not a particularly controversial observation, except for really sort of diehard TDD fans. But, testing is a risk-reward kind of operation, and you should test until you reach a point of diminishing returns. Fortunately for Urbit, we can actually do deterministic unit tests on the entire operating system as a whole. Isn't that nice? Yeah. So it's another win of functional programming, which actually brings me to my next point, which is that, so I'm going to kind of go back to my original framing here and talk about where I was talking about what do you want to do differently or how do you want to design your code if you want it to last forever? And a lot of the answer to that concerns the environment in which your code runs. And this is sort of one of the core theses of Urbit, is that a lot of what's wrong with modern software isn't really the code itself, but the environment in which that code needs to execute. And so what's wrong with the environment? Well, it's not repeatable generally. So it's not deterministic. It's like if you run a piece of code twice, it might do two different things. A related issue is that there tend to be implicit dependencies in pieces of code that depend on the environment in some implicit way. So often there are some variables that you can read from or even write to from within a routine, and it's not necessarily obvious that that routine is affecting variables that also are read from or written to in some other routine. So you can get a sort of spooky action at a distance where you think you're just running one function, but actually that can change the behavior of some other function. Or I should probably say routine here, because in mathematics, a function means something with a defined set of inputs that when you run it on those inputs produces a particular output. If you ran it again on that same set of inputs, it'll give you exactly the same output. And of course, in math, that's all that a function does. It's a mapping from an input domain to an output codomain, right? So it's not something that does something, right? A function doesn't do anything. You give it an input, it transforms that input into an output, and you can look at the output. If you're running the function, you can look at the output and decide to do something with it. So there is a school of thought in programming called functional programming that uses functions as the sort of main unit of control flow, main unit of organization of the execution of a program. And because they made the observation that actually, having your code not actually do anything, not be able to affect any global state, right? It can't actually have this spooky action at a distance. And it is repeatable because you have to actually specify all the inputs, and all you can ever do is run a mathematical function that is guaranteed to give you the same output based on those inputs. And that guarantee comes from the way that thing is constructed, because each of the operations you do is purely functional. And so there's just no way of expressing something that isn't purely functional. This is a great idea. And the Haskell people and some Lisp people, and now many other languages, Clojure, Scala, F#, ML, Camel, there are all kinds of languages that give you a lot of facilities for working with pure functions and can do a lot of really great things based on the fact that all you're ever working with is pure functions. Urbit is also one of those systems, but Urbit takes it a step further than anybody else And the way that it takes it a step further is by saying that the environment is purely functional. The environment in which your code runs is a purely functional environment. Well, what does that mean? It means that when you write some Hoon code that compiles to Nock, and that includes the Arvo operating system, all that code can ever do is take in an input and produce an output. There is no global state that gets modified, and there is no spooky action at a distance. And what this means is that that sort of pure functional paradigm is actually pushed all the way to the edges of the OS. So it's a functional operating system. This is why we sometimes call this an operating function. And for those of you who are not programmers, no, this is not the way that that operating systems are usually defined. Not in the slightest. The most standard way of writing code, and the way that modern processors, expect for code to be written, is as a sequence of instructions, a sequence of machine instructions. If you hear about a 64-bit processor, that means that each of those instructions is a 64-bit number in memory, and basically the way the processor works is it starts at the beginning of the program, reads that first 64-bit value, runs it, and then moves to the next one and runs that. And the way you have a loop is that there's some of those 64-bit values, say, jump to some other location. So you can jump backward to the beginning of the loop, and then it'll start going through in those machine words in sequence till it hits the end of the loop again, goes back, right? So most programming languages are basically sort of more concise ways of expressing that form of machine code. So these are called imperative languages. It's called imperative, meaning command, right? Because you're giving the machine a command. You're saying, do this, do this, do this. For non-programmers, I like to describe it as like a recipe, right? A cooking recipe. So most programs are sort of like recipes where you say, there's a list, an ordered list of here's this first thing you're supposed to do, here's this next thing you're supposed to do. So most operating systems are written in computer languages that still let you express the program in that way. It's still expressed as a sequence of instructions. Functional programming is not that. Functional programming means that your language lets you express your program as a mathematical function. So you're just defining the function. And there's something that runs that function that somehow interacts with the processor. So in Urbit, that thing that interacts with the processor, we call it var. So that's the runtime, or the virtual machine. Different technical terms for the same thing in our case. And also called the interpreter, because Nock is a language, right? Nock is our machine code, and that language is interpreted by var, which is another program. That program is written in the language C, which compiles down to machine code that a processor understands. So Urbit's sort of a two-layer system on modern processors, because code in Urbit is expressed as a pure function from input to output. And then because modern processors don't know how to run code that's defined that way, all they know how to do is run a sequence of 64-bit machine words. There's a program that's written as var. There's a program var that's written as a sequence of machine words that is responsible for running the function, right? Running Nock. So it interprets the Nock code and runs it as it sees it. And so that interpreter is also responsible for constructing the inputs to the function and delivering them, right? So it says, okay, something happened. So those inputs are events in Urbit, and the outputs are effects. The output is the effects and the new state. So basically, the standard way that we define this is we say that Urbit, the operating function, takes as its input the old state, so the old Arvo OS, and a new event, which is, something happened, right? Maybe a key was pressed or a packet came in over the network, packet of data. And so the inputs are the old state, the old Arvo OS, and this new event. We run Nock on that, and what comes out is a pair of a list of effects to be performed and the new Arvo. So then the next time a new event comes in, we use that new Arvo as that half of the input, right? So we're threading through this changing Arvo state from event to event, and then the effects that come out of running Nock, that's a list, and it's a list of data structures, trees that describe what action should be performed. So that action is something like, emit a packet over the network, or write a character to the terminal, to the command line, or send an HTTP response back to your browser. So every time, what it means to run Urbit means that there is this program var that knows how to run the Nock function, and it knows how to do a few other things. It also knows how to take input events, such as key presses and whatnot, translate those into Nock nouns, right? Nock trees, and then run the Nock function on that input and the old Arvo OS, which is itself a noun, right? So it knows how to run Nock on that, and then it knows how to take the result of running that Nock and extract the effects and extract the new operating system, hold on to that new OS so that the next event can use that, right? So that we run it on that so that the operating system can actually can change its state over time, right? This is a stateful packet transceiver is one way to model this. So it means that the operating system, this whole idea is that you have this Excel file type thing, right? Going back to the first episode here, you have this thing that's like an Excel file. It's a piece of data, and it updates itself over time to store all of your files in there and store all of your programs and know how to run those programs and know what those programs are in the middle of doing. So all of that is encoded in this Arvo OS, which is itself just a noun, just like anything else. But that's the noun that gets threaded through executions of Nock by var, right? So var runs it runs the new event on the most recently updated Arvo OS. And then after it runs this event, it stores the new Arvo OS and it looks at the list of effects, and for each one, it actually goes and performs the action that's specified by that effect. So you might have an effect that looks like a pair of send HTTP response and some piece of data. And so that send HTTP response is a string of text, and var will look at that and say, oh yeah, okay, so I know that when I see HTTP response, I'm supposed to actually call run some routines that send an HTTP response out over the network. And so var typically at the moment, var only runs on Mac OS and Linux. So it uses Mac OS or Linux to actually send the HTTP request or HTTP response, because those are things that you normally need a a modern operating system to do. So this is how Urbit overlays over modern operating systems. The other thing that Ver needs to do is write the event to disk. When a new event comes in, it has to write it to disk to store it permanently. And that's so that that's part of how this system is sort of restartable, because you need to be able to shut down the computer or even yank the power plug out of the computer and then restart it, and your Urbit needs to pick up from where it left off and not forget anything that it's done. So this is the same requirement that databases have. And actually most modern applications use a database to store their information. So in Urbit, there's sort of, like another sort of analogy for what Urbit is we took an operating system and we stuffed it into a database. And so because we write each event to disk, and there's a deterministic mathematical function for how to obtain the new state of the operating system as a function of that sequence of events, then all we have to do to sort of reinflate the state after something crashes, right, or after your machine gets turned off, is you just replay the events as if they're happening for the first time. Although we don't emit the effects because we don't need to. But we run that event, we extract the state that comes out of running that event, we use that to run the next event, and we do that over and over again until we've run all of the events that have been written to disk, and now we're up to date. As an optimization on this, we also take a snapshot of the full Arvo state once every 10 minutes or so. So we write out the entire Arvo state to disk. We actually do that in an incremental way so that we only write out the pieces of it that have changed since last time. And that way, instead of having to rerun every event ever, we just have to rerun all the events since that last snapshot, which is generally much faster. So Ver is also responsible for maintaining that persistent state. This is different from other functional systems. Remember I was saying that Haskell and Lisp and other functional languages, they let you write code using pure mathematical functions. Right? So, okay, well, do they also do this thing then, or where they have, when you write your code, it's just it runs as a function going from input to output, and then there's some system that translates, that into something that a processor understands, and then, records what happened so you can run it again. No, oddly, Urbit's basically the only thing that does this, despite it being sort of an obvious design in some sense. So Haskell, sort of the flagship pure functional language these days, and the way it works is it uses something called the I/O monad. Monad is a mathematical term, but really what it is you can think of it as there's a certain special data type representing the real world, and it's never instantiated, but Haskell uses this sort of clever trick to make it so that you can express a sequence of functions that take in that real world and output a new real world. And then some of those functions are special, and so they can actually cause the runtime to emit an effect when that happens. So there's like let's say there's a print command. There are a few different ones, like print line, right? Print a line to the, I think it's called put sterlen in Haskell, but that writes a line to the terminal, writes a line of text. The way that actually works is that takes in this, the text that it's supposed to write, and also the this sort of imaginary real world variable, and then all it outputs is a different real world. But actually that function is special, and the environment that you write your code in knows that that function is special. And so it knows that it will actually cause this imperative action to fire, right? It'll actually it'll perform this effect when that function is called. And so basically what Haskell is doing here is it's giving you this sort of facade to work with as a programmer, where all you ever write are these pure functions, including the functions that do this I/O, this input and output stuff, where sure, like it is technically a pure function that you're writing, but actually these side effects happen as a result of running that pure function. And the way those side effects happen aren't part of your specification. They're not part of what you're writing. That's set by, those side effects are determined by the system itself. So it's not even really Haskell the language that encodes these special functions. It's really that GHC, the primary compiler for Haskell, has this particular I/O monad as part of it. Maybe that's technically part of the language, I'm not sure. But it's not part of what's called the pure subset of the language. It's not functionally pure in some sense because it's actually performing effects. Now, you might say, okay, well, and I think Haskellers generally would say, well, what's wrong with that? You're still expressing your program as a pure function. And yeah, some of those, there's this sort of trick here that lets you express sequences of input-output actions. But that's still done in a way that could be deterministic, sort of. It's technically non-deterministic. They'll call it non-deterministic. And that monads are how you embed non-determinism into programs, into functional programs. And these things all get very fuzzy, really. It's well-defined to some extent. At least the sort of pure functional side of it is well-defined. Like, you really are writing a pure function from the perspective of the inside of the system. But in practice, it means that that Haskell code is run in an imperative environment, right? There are these hooks. And what does that imperative environment let you do? Well, actually, it lets you do basically anything. So, you can manipulate memory, right? The RAM of the machine. You can call arbitrary host operating system calls, right? So anything that Linux lets you do, you can do that from inside of Haskell. And so Haskell itself, like that one Haskell program, is purely functional, but it's interacting with the host operating system and with other pieces of code in a way that's very open. And so you can do all kinds of non-pure functional things from within Haskell. And in fact, this is the standard way to make basically anything run with decent performance, right? So Haskell has all kinds of things like it has a software transactional memory system, for example. How does that STM system work? Well, it uses a lot of void pointers in C, right? Basically, then there's a sort of pure functional facade that's wrapped around that. And this is generally how Haskell works, right? There's a pure functional facade for manipulating sort of arbitrary external pieces of functionality. And so if you were going to try to put together a full specification for exactly what a piece of Haskell code does, you really can't do it because it might depend on what host operating system you're running it on. So if you were to write something like Urbit in Haskell, it might actually do different things if you moved it from machine to machine, right? If you moved it from Mac OS to Linux. It's just Haskell was really not designed for this at all. It is really not the point. The point of Haskell primarily is to allow programming language researchers to develop new features, and it's been a really outstanding success at that. But it's not really designed to be repeatable, deterministic, or fully specified. So it really doesn't meet the goals of something like Urbit, where we want a piece of Nock code, a piece of Hoon code to mean exactly the same thing forever, no matter where you run it. So again, this difference between the environment in which Nock and Hoon code runs and the environment in which basically everything else runs, that difference is downstream from the difference in perspective and the difference in goals, where we are trying to say this piece of code will always do the exact same thing forever. And that's a useful property for us because we're trying to actually make an operating system whose functionality is frozen in stone forever. As opposed to trying to write a piece of code that can be changed as often as possible. In fact, Haskell, the language, is designed to be changed as often as possible. There are hundreds of language extensions for Haskell that people use to experiment with new programming language features. Some of them are very cool, very sophisticated. And Haskell itself is designed to be extensible with those features so that people can add new features and continue to change what Haskell code means, basically. So, again, very different approach. Their approach is sort of more like agile development, but at the level of developing a programming language and interpreter, or compiler. Well, they have both. But I'm going to take another tack here, actually. So another thing that's interesting about Urbit, and sort of one way of thinking about it, is what we call a solid-state interpreter, which is not a standard term. But solid-state, you can think of it like a solid-state hard drive, and it basically means a piece of electronics that sort of doesn't have moving parts other than electrons flowing through it. So a processor is solid-state. A solid-state disk, solid-state drive, an SSD, is also just a piece of electronics that you have to store your bits, as opposed to a hard drive, hard disk drive, which actually has a motor that spins a piece of machinery, or it spins this disk and then reads and writes to that spinning disk. So that's not solid state. So when we say solid state interpreter, what we mean is, and we say Urbit is a solid state interpreter. And what we mean by that is that it's sort of just an analogy where the idea is you don't need to have, you could write a var that's implemented pretty much completely in hardware, where there isn't really any software running. You could write a processor that basically all it does is run var. And again, this is different from, say, Linux. There are actually some attempts, I believe, to run at least parts of the Linux kernel in hardware. And of course, actually big chunks of it end up getting run in hardware, such as TCP modules. This is the reason networking can go so fast on modern computers is mostly that a lot of it gets offloaded into hardware and run in so somebody will write an application-specific circuit, an ASIC, that all it does is knows how to send and receive TCP packets. Sort of interesting. It's very interesting, actually. And there are actually lots of ASICs or really components, hardware components on modern processors that do very specific things. So these are called accelerators, typically, by processor manufacturers. And they're also called IPs because they typically refer to one sort of unit of intellectual property. So you might have one IP on some chip that implements a particular encryption routine, or implements a particular hashing routine, or implements something that lets you do very fast floating point operations. And a modern processor, a large modern processor, like an Intel or an AMD, typically has many of these IPs, and an increasing number of them, actually. So they'll have many different accelerators that are on the chip. So in addition to having the major processor cores that are general purpose, where you can have them run any code, those are the 64-bit cores, right? You say it's a 64-bit processor, and they're executing these sequences of 64-bit instructions, right? So there are those, and then there are also this smattering of accelerators, each in their own IP, their own sort of their own block of transistors, in a separate part of the chip. And so modern chips are increasingly heterogeneous. You might hear the term heterogeneous computing. And they have an increasingly large number of these IPs. And part of the reason for that is that each transistor is getting so small that you can just fit a ton of transistors on the chip. And so just sort of in order to make use of all that real estate, they'll say, all right, well, let's stick a bank of adders, a really big bank of parallel adders or something like that. Let's stick that here because we have so much extra space. Whereas it's hard for them to make it just go faster, mostly because of heat considerations, is my somewhat outsider understanding. But in any case, you get this heterogeneous compute world, and this is good in a lot of ways because you can, do a lot of things faster, right? And you can make use of all this extra real estate on a chip, have better energy efficiency for those more specific operations if they're run using a dedicated circuit compared to trying to run them on, a general purpose CPU. So all those things are good. But the bad side is that when a programmer is writing code, they have to figure out how to have the main processor communicate with each of these IPs, each of which tends to have its own interface. So the instruction set, the ISA, the instruction set architecture, the ISA, that you use, that's nominally all that you need to know in order to write a program for an Intel or an AMD chip. Right, so the ISA is x86-64. That's the name of it, and there are a few thousand operations that you can do, different 64-bit words, and the idea is that ISA is all you need to know in order to write a program, because you just express this sequence of 64-bit words, and then that specifies what the processor is supposed to do. So okay, there are a fair number of those commands, but a compiler, somebody writing a compiler from C or some other language down to that machine code can learn what those are and figure out which ones to use. And then anybody writing C code will be able to take pretty good advantage of the processor. However, it turns out that ISA is not enough to really use the processor as a whole, because there are all these different IPs, and in order to talk to them, they don't understand that ISA. Each one has some bespoke communication protocol where you can't just give it the same set of 64-bit words and expect it to work. You have to give it some other thing, and each one is different. And they keep changing. And also different chips have different sets of IPs. So now, if you, as opposed to, there are many different, Intel and AMD chips, even made by different manufacturers, right? Those two different ones. With all kinds of, some are bigger than others, some have more cores than others, but they all implement the same ISA. And so you can write code once and it'll run on all of them. So this is becoming less and less true. So basically, now there isn't even really a standard for how you communicate with the processor. There's a standard for how you communicate with the main core, but if you write some code that also, sends commands over to some, maybe like video decoding chip, well, actually, that might be running on a processor that doesn't have that video decoding chip, or that video decoding IP, that accelerator. And so that just won't work. And so there's a big concern in the industry that it's becoming harder and harder to take advantage of all these extra processor features. And there's this sort of Tower of Babel problem where you don't even really know, what's going to work and what isn't. So oddly, Urbit provides a way out of this because, and this is a very technical point, but it's actually kind of a deep one. So one of the ways that var, the Urbit runtime, gets Nock to be run at an acceptable speed is that it uses what are called jets. So a jet is a function that var has internally that does the same thing as a piece of Nock code, but does it faster. And so the idea is sort of like a jet-assisted takeoff of an aircraft. You can look at videos of a C-130 cargo plane doing a jet-assisted takeoff. They're pretty cool. But the idea of a jet is the usual example that we give is the decrement function. So Nock, our machine code only exposes, and the only mathematical operations are check equality, so check if two numbers are equal, and increment, so add one. And you can do loops. So it turns out that you can build all of math out of those operations by running a loop. So decrement, for example, which is not built into Nock, if you want to decrement some number, you can start at 0 and increment 0 until increment 0 n minus 1 times. And so then you can check if you incremented it again, does that equal the number that you gave it as input? And if so, then you've decremented it, right? Okay, that works. Like that is a correct definition of decrement. But it's incredibly slow, right? Because you'd have to check n minus 1 numbers just in order to subtract 1 from something. Compare this to what a processor does, where there's a built-in subtract 1 from this. All right, like I think decrement is actually built into a lot of machine codes. If not, you can subtract 1, and there's a dedicated circuit for subtraction that'll run that very quickly, extremely quickly. And the asymptotics are better, so that basically instead of running something n times, it only ever runs it once. So it doesn't take longer with bigger numbers. So there are a lot of things like this, right? What if you want to add two numbers? What if you want to multiply two numbers? Processors have built-in support for doing those operations. Those are some of the 64-bit words, right, that the processor understands. There's like, hey, multiply this number and that number. And then there's a dedicated circuit, usually many banks of these dedicated circuits that say, okay, take these two numbers and multiply them. So that circuit can multiply those numbers way faster than this, loop that adds 1 to something over and over again. So we don't want to use the, while we can define this in Nock, and it's good to define it in Nock because Nock is axiomatic, right? We want to have this full specification of exactly what the code does. And we want that specification not to have external dependencies that could change depending on what operating system we're on, right? So yeah, we want to write decrement in terms of Nock, just in terms of numbers and check equality and increment and loops. And those all of those concepts are built into Nock. You don't need to know which operating system they're running on or anything like that in order to know what answer is going to come out of there. It's fully specified, very tightly specified. That's good. We want everything to work that way, actually, right? And so, but we don't want it to be slow. So, okay, how do we fix this? Well, we use a jet. So var, just one of the things it knows is what the Nock code is, the standard Nock code for decrement. And so whenever it encounters a piece of Nock that says run the decrement function, which is some of this particular tree, then var looks at that tree and says, actually, I know that exact tree. That's the tree for decrement. So I'm not going to run that. I'm going to use the processor to run decrement. So as long as var is written correctly, then it just runs decrement using the fast processor version, and voila, there's the answer. So this is something about Nock code, is that we call it an executable specification. And it really is. The idea is that Nock just specifies what the answer is supposed to be. It doesn't say how you're supposed to get the answer. I mean, it will give you a recipe for getting that answer, but you don't have to use that recipe. You can get the answer however you want. And as long as you get the same answer that Nock gets, it's legit. So we have lots of jets. We jet almost all the arithmetic functions. And we even jet some of the list manipulation routines and some other things like that, where we can do a loop faster. We can kind of shave off some of the extra performance overhead of running Nock by doing some tricks based on how modern processors work and how modern operating systems work. And because var, there's a different version of var for every platform that it runs on. That can do whatever tricks it wants to do on that platform, right? On that processor, on that host operating system. And that's fine as long as it gets the right answer. And it's easy to check whether it got the right answer because there's a very, very tight specification for what the right answer is. And that's the Nock code. Now, it's not necessarily easy to programmatically verify and prove that it does the right thing. And so you don't want to have too many jets. You don't want to have jets for really complicated things. So there used to be jets for a text format called Markdown, and that text format is actually so complicated, has so many sort of little details and little things that aren't tightly specified, that it's very difficult to write a jet that actually matches the spec. So there are different things you could learn from this. One is to say, all right, well, it's a limitation of jets, which it is. But it's also a condemnation of a spec that isn't tightly specified, right? It's like, if you can't jet it, well, then you probably can't make it timeless, right? You can't ensure that different implementations, if you can't ensure that different implementations actually meet the spec, it's not a very good spec. You should specify something else if you want it to last, right? So Urbit, maybe it's fine for that in general. Maybe it's fine to have a spec like that, but it shouldn't be in Urbit because it can't be made to last. And so it's not exactly a fault of the jet system, really. Maybe parts of it are, but it's a little deeper. It's a deeper fault, really. It's saying, okay, well, that's not something that can really be run in a repeatable, deterministic manner by different pieces of code. And if that's not the case, then that's not something that should be in your personal digital archive that you expect to pass on to your descendants, right? It doesn't meet the requirements for that. So you don't want too many jets. You don't want jets for things that really aren't tightly specified. But you basically want a jet for anything that the processor can do faster than naive Nock code can do. So arithmetic operations are good because processors have lots of support for various specific mathematical operations. So those are going to go much faster by just using the processor's accelerator. For math, usually called the ALU, the arithmetic logic unit. There are also vector processing units, all kinds of other things built into modern processors. And coming back to this problem with IPs and ICEs, when it comes to writing, say, a hash function, or a video decoding function, or a anything where you might actually have an ASIC for it, or sorry, you might have an IP for it, or you might have a dedicated accelerator for that particular routine. You can just write that routine in Nock, and then if there's an accelerator for it on the processor, then you can jet it with that. And so Nock really becomes an ISA, and it becomes an extensible ISA. It's really Nock plus the set of jets, right? The set of standard jets. And so there's a very interesting way in which, so this goes back to this idea of having an extensible standard, right? I said at the beginning of this, Urbit is a way of standardizing how you can extend a computing standard to give it new functions. It's like, okay, well, you specify those functions in Nock, and that depends only on the only thing you have to know to really have a very formal understanding of what that function is supposed to do is the idea of an arbitrarily sized natural number and the idea of an ordered pair, which everybody can agree on. And then there's some function written in that way, and you can either run that directly, right? Run it in Nock, actually run the Nock code step by step. Or if you have some faster implementation of that, such as an accelerator for that function, then you can just use that accelerator. And so now Nock sort of becomes the ISA. And it's extensible, but you can just write the code as Nock, and then if there is a jet for it, that'll run. That'll use whatever it thinks is the fastest way of running it. And if it doesn't have a jet, well, then it just runs the Nock. So, okay, maybe it's not as fast as if you had the accelerator, but when you want to run a hash function, you want to run the hash function. If it's a little slower because it doesn't have an accelerator, then so be it. But you still get the right answer, and it'll still run. So, there is a set of jets without which Urbit really won't run on a modern processor, right? Because it'll be too slow. But we actually don't really want to specify that set because different interpreters can use different tricks. They might be running on different processors. On certain processors with certain interpreters, you might have a different, set of tricks that you want to run, and that might mean that maybe you want to jet the list functions on some operating systems and not on some other ones. Or it's really more likely that based on the internal design of the Nock interpreter, some Nock interpreters are actually just fast enough that there are certain things you don't need to jet. So, for example, the main implementation of var uses a bytecode interpreter for Nock, which is so basically it actually translates Nock to a different language and runs that so that it can run it faster. That's actually fast enough that we were able to turn off and remove a lot of jets that used to be required. But now they actually, once the interpreting Nock code got fast enough, then we actually didn't need those jets at all. So those, some other interpreter could come along and write its own jets for those if it was too slow in that particular way. So it's not prevented from happening in the future. But we don't need it. So as long as everybody's running the same spec, right, and can agree on what the spec is, then it's valid. Right? So this is what Urbit lets you do. Urbit lets you provide a timeless specification for what a program is supposed to do. And yeah, some machines are going to run that faster. Maybe something is running on a host operating system that uses some specific trick. Maybe it's running on maybe you have some other implementation of var that runs on some weird processor that doesn't exist yet. Maybe it uses a different set of tricks. And eventually, you could imagine having a sort of physical instantiation of a solid state interpreter where you have a chip that actually just runs Nock, and it has a separate IP for each jet. Such a chip would probably be very efficient. It would be fun to work on. Nobody's done it yet. It's a big project. It's a research project. But that's the kind of goal, that's the kind of world that we see happening, right? You can't really do this with Linux. You can't really write a chip that implements the entire operating system. But with Urbit, once the Kelvin versions get down close to 0, you could very well imagine doing this, getting big speed ups, and in general, just having a much sort of saner, cleaner, and more standardized environment in which code can run. So we want to provide this sort of stable basis, stable environment for code that lets you write your own code in some way, right? Like in a way that's also tightly specified, repeatable, can be built repeatably, right? Like when you turn the source code into a program, you know exactly what's going to happen there. When that program runs, you know exactly what's going to happen there. And you could write new jets that are just for that. So sort of building block by building block, you know, jet by jet, and specification by specification, so module by module, we are constructing a standard for the behavior of computers. And that's a standard that can be implemented in software on modern systems, and eventually, probably mostly in hardware in the future. But that standard doesn't need to change. And so we don't need to use agile development techniques. In fact, we use a very different development standard. And our version of timelessness means freezing a component. So we factor out the pieces of software that don't need to change, and we get those right. So how far along are we on this process? Well, Nock is at Kelvin version 4. We're pretty close to getting that right. Nock in practice is fine. We don't know of really anything that we need to do to change it. Last time we changed it was, I think, about 2 years ago. Went from version 5 to version 4. That made a few changes. And since then, there hasn't been any clear reason that we would need to change it again. And the Hoon language is at version 140. There are some things that we probably want to change about Hoon. It would be nice to make the compiler faster. In order to do that, we might actually need to change the language some. There are some rough edges in the type system, so we'd like to smooth over some of those. It's unclear how incremental that work needs to be. And there are a few pieces of syntax that need to get added. There are a few things that need to be cleaned up, and it would be good to have our printing functions be cleaned up more. My suspicion is that by around version 130 or so, Hoon will be maybe 115. We'll see. That Hoon will be pretty stable, and we won't even really want to change it that much. The Kelvin budgets are surprisingly sort of generous, actually. They don't seem like that much, but in practice, often don't have to change things too many times in order to get them pretty stable. The vanes themselves and those are the kernel modules that implement input and output and application running. Those still need some work. In particular, the application runner and our file system, I think, are the ones that need the most work. And I think we're going to make 2 or 3 big changes to the networking. We'll probably add a second kind of networking and do some cleanup on the original kind. But actually, the overall architecture of most of the vanes is quite stable. So we have a pretty clear picture of which pieces of that are going to need to change. And so we still have our work cut out for us, and there's still a few hundred versions that we have to play with over the next few decades. But we are zeroing in on a timeless standard for what it is that your computer does, so that we can all agree on how these things should work, how they should talk to each other. And even though my computer might be running a very different set of applications from yours, they'll still be able to communicate with each other over the network, and they'll be able to adapt to the changing world by having a firm, stable foundation upon which to build apps and build protocols. Thus concludes this episode. See you next time.